Alrighty, so for I do now, we are going to find out this differential equation. Solve this differential. So pause this video, solve it out, and there are going to be some unknowns because we don't have any specifics. For instance, if you had like a point, you could find an exact solution, but you don't. So go ahead and give that a try. Alrighty, so just to see this differential equation, it seems that the slope increases as we go up in y, meaning that at y equals 1, we have a slope of, let's say, 0.3. So that's go up 3, go to the right, 10. I'm going to go ahead and guess that's something like this. And then as you go up, it goes a little bit higher, a little bit higher, a little bit steeper, a little bit steeper. Anyway, so when you're at, let's say, 10, your slope should be around 3. So let's say over here it's 10, so we have like a 3 slope. So along the y, it's going to be the same slope. My drawing is pretty bad. And then around over here, we have the same slope. And then in between, we have like this kind of slope. So the slopes are different at different stages. Since we don't have any specific points to find the exact equation, I'm just pointing out that the equation will be different at any given point. For instance, we can have something like this, you know, maybe use a different color. We can have something like this, something like this. Would this be correct if you were to continue doing this process? Pause this video, think about it, and then press play again. So if you plug in negative y's, meaning you'll be underneath the x-axis, then you would have negative slopes. So this is actually down here incorrect. It should follow a similar path, but in the opposite direction. You know, as you go further down the y, your slope is going to be steeper. And if you, let's say, have -6, if you plug in -6 in there, you're going to get a slope that is -6 times 0.3, which is -1.8. So down there, at 6, we should see something like, I'm trying to be between slope of 1 and 2, something like this. So you can see that this slope right here at that point does not correlate with what's happening with these lines. So if you pause the video and you were like, hey, you know what? These right here make sense. Let me just not do what I just did. It's going to look ugly this way. If you said that these make sense, but however, these seem like you get a positive slope at the negative y's, but if I have a negative y, shouldn't I get a negative slope? Then you did the right thing. Then you pretty much noticed that there's an issue right there. Alrighty, so, by the way, we didn't even do the problem. If you do the problem, you have to first separate it, so let's do that. So you pretty much trying to get y by itself with the dy. So multiply dx on both sides to get dx on this side. Divide by y to get y by itself. Do your integration on both sides, and you should end up with a natural log of y equaling 3x plus c. Now if you're trying to get y by itself, we can't really get specific answers because we have like these constants right there. When I say these constants, what I mean is you're gonna have like a c. And there were 2 constants, it's combined to 1. So when I say constants, there was a constant here, there was a constant right there, it got combined into a single constant. Anyways, let's solve for y because we can't really solve for a constant. So e to the power e on both sides, that cancels out this natural log, you get y equaling e to the power of 3x plus c. You can separate this by having e to the 3x times e to the c. This now becomes its own little constant, and we tend to put the constant up front. And this is as far as you can really get. Without having any like initial values, you can't exactly solve for whatever that c is. But you can see that this is the equation that kind of fits these right there. You know what I mean? Except you should have this reversed down here. These should be reversed, but you can see that this is an exponential function. You're probably wondering why I spent 2 minutes in the beginning of the previous slide to talk about what the slopes are at different points. The main reason is because we're going to start talking about slope fields. It is exactly what it sounds like. You're pretty much trying to find out what the slope is at different points in the x and y axis, and this will represent the slope field. It kind of gives you a trend where a function would flow. For instance, just looking at this, I can tell a function would kind of look like this at any given moment, you know? Just following the flow, kind of like a river. Here's a little illustration. How it kind of follows the slope lines. And we're going to talk about those. So that's pretty much why I spent all that time talking about it. For the specific given, to find an equation for it, dy dx equals this particular solution at 2e to the 0x. So we can actually find the exact solution from here. Or we can just find the exact slope. But we can do this problem now. So let's separate the x and the y's. So we have this. What are they doing? Why are we only finding the slope? Given that, particular solution that. Now let's draw these short segments for all the solutions to the differential equation. Okay, I don't really see the question here. Alright, for some reason they were only interested at that particular slope. So at x equals 2 and e to the 0.6, we had this slope, which is very true. Okay, so that was that. Also notice that along the, I should have probably talked about that too before I said we're going to move on. Notice that at any given line, y line, the slope is the exact same. That's because the dy dx is only dependent on y. So even though we were given a point that has an x and a y, the only thing we really needed to plug in was a y. The slope at that particular line is going to be the same thing, 0.546. Alrighty, let's move on. For this problem, we have two things they want us to do. First, they want us to graph all of the equations that have this derivative. So, it's very x-dependent, meaning the derivative will change by x. So as I go to the right to x, I'm going to get a more positive slope. And as I go to the left of x, I'm going to get a more negative slope. So you can kind of see it right here. I mean, there's some sample points you can do. At 0, we have a 0 slope. At 1, we have a 2 slope. At 2, we're going to have a 4 slope. So when you make a few lines like this, it should look something like this, and it becomes more and more steep. Then it says find the graph at 0, 2. So at 0, 2 right here. Let me change the color. If you go to the right from 0, 2, you can see that your line would follow this trend or flow, and to the left it would follow this flow right here. So pretty much you have a parabola that you really got. So whenever you have like the initial point, you put that point that's clearly part of your graph, and just go to the right and to the left and see what happens. Where does it take you? Where does the slope field take you? So this is a parabola right there. Let's move on. Let's read this problem. So if you have a differential equation right here, you can see that there's already a slope line kind of drawn for you. Use the differential equation to find the slope at the points BAM and BAM. Mark these points on the figure. Explain why the calculated slopes are reasonable. So we're going to do that. And then for part B, it's going to be start at point 0.6 and draw the graph that represents a particular solution of the differential equation that contains the point. Go both to the right and to the left. What geometric figure does the graph seem to be? And then start at point 5.2 from part A and draw another particular solution of the differential equation. How did this solution related to that in part B? And then solve the differential equations algebraically, find a particular solution that contains the point 0.06, verify the graph really is in figure indicated in part B. Ironically, you're probably going to be more comfortable doing this part right here, because this is the stuff you did in 7.2. But this is actually kind of easy because you're just drawing. That's pretty much all you're doing. But let's start with part A. I'm going to go ahead and stop the recording so I can start doing some stuff. Alrighty, I found my two slopes for the first one. The 5.2, I got negative 0.9. And for the second one, I got me 0.347. So one is a negative slope, the other one is a positive slope. So let me just read. Use the differential equation to find the slope at points, blah, blah. Mark these points on the figure. Explain why the calculus slopes are reasonable. Alright, so let's go ahead and mark it. So at 5.2, so 1, 2, okay, 3, 4, 5. At 5.2, right here, you have negative 0.9. That's very reasonable. I mean, look at that. This line pretty much looks like negative 1. So it's very reasonable, being negative 9. Now, for the next point, for this point, I'm going to be expecting a positive slope, which is roughly half, like 0.5. So let's check that one out. So negative 8. 1, 2, 3, 4, 5, 6, 7, 8. And we're going to go up 9. 1, 2, 3, 4, 5, 6, 7, 9. Okay, I'm gonna go ahead and guess it's like right here, right there. They all pretty much look the same at this point. Yeah, I have a positive slope, and a positive slope is like a half. So they're both very reasonable. They look like the field line suggests. Okay, so let's start doing B. I'm gonna go ahead and pause it and do it. Alrighty, turns out I don't really have to do any calculation. I just have to start at 0.6. So, okay, be right here, 0.6. If you go to the right, you can see that due to these electric field lines, it's kind of pushing me further and further down because the field lines are going further down as well. So just make these little lines and then you can pretty much see what the picture is going to look like. Alright, so that's pretty much becomes an ellipse. Go both to the left and to the right. The geometric figure seems to be an ellipse. Starting of 5.2 from point A, from part A, 5.2. So 1, 2, 3, 4, 5. 1, 2. Okay, so we're like right here. I do the same thing. Just follow where the lines tell you to go. My drawing's not gonna be the best because I'm literally looking at each line as I'm doing this, and my pen that I'm using is not okay. I went way too far high right there. Okay, doesn't matter. Follow the cards. Follow the heart of the cards. Okay. Anyways, so that was that. Starting point 5.2, part A, and draw another particular solution, differential equation. How does the solution relate to part B? It's the same, just smaller. You know, you can see that it's just going to become smaller as you go towards the center. And then yeah, we finished that, and now we actually do it algebraically. So go ahead and pause the video. Try it algebraically. You should have some background knowledge on how to do it, and then compare with what I get. So I did it algebraically. So I needed to get my y's and x's with the dy and dx respectively. Took an integral on both sides, ended up with this good stuff. Now I could have done what the book usually does, which is solve for y first and then solve for c. But you don't have to. I purposefully solved for c right away. So I plugged in this point and the y and the x. This is just 0.18 times 0, which is a 0. And I got my c being 18. The only important thing is, given that I plugged it into here, you want to put the c in here, which is what I did. Given that I was kind of looking for a ellipse, because that's what the graphs kind of look like, I first went ahead and multiplied by 2 to get rid of whatever is from the y squared. Then I divided by the 36, and I actually didn't finish, so my apologies. 36 divided by 36 is 1. So I divided both sides by 36 in order to get something that kind of looks like an ellipse. And if you're wondering why that looks like an ellipse, it's because if I take this to the other side, wait a second, I made a mistake. Let me just fix that real quick. That's a negative I didn't carry over. So that's negative x squared over 100. So when I carry to the other side, so I get y squared over 36 plus x squared over 100 equaling 1. That right there is an ellipse that tends to stretch more horizontally than it does vertically because the bottom number is bigger. Alrighty, that is it. So what was that? Did answer the question, by the way. Verify that the graph really is a figure indicated in part B. It is. I can graph it and then it will actually follow it. You see that these graphs are ellipses. So if I was to graph this one, I will get a graph that will fit and the slope field line. I do not want to make this video any longer than it already is. So what I would like you to do is pause the video and actually do this problem right here. It's very similar to the other problem we just did. And I would also, after you did that, do this problem as well. So go ahead and just pause the video, give them a try, and then I'll talk about it in class. And I'll just check how you guys did on it. Alright, that being said, see you guys tomorrow.